Alright, today in this section 7.5 we'll be covering exponential and logarithmic equations, solving logarithmic equations, solving exponential equations, and solving problems involving exponential growth and decay. Equations with unlike bases. Earlier in the chapter we solved equations where we could write both sides with the same base. Frequently we want to solve equations where this cannot be done. For example, 2 to the x equals 7. We do know that x must be something between 2 and 3 because 7 is between 2 squared, which is 4, and 2 cubed, which is 8. But in order to solve this more precisely, we need to get the x out of the exponent. The power rule, log base a of x to the r inside the logarithm, equals r times log base a of x, is the key to solving this type of equation. Alright, so looking at this first equation here. Now, when students see something like this, the first thing they try to do is divide the 5s out and divide 5 into 30. Please don't do that, because we can't do anything with this 5 because there's an exponent that has an unknown. So the first thing we need to do is take the log of both sides. So the log, and we'll probably do log base 10. You could do natural log. Either way would be fine. So I have log of 5x, log of 5 raised to the 3x equals log 30. So now I'm going to move that 3x out front as a coefficient. So that's going to be 3x times log 5. Remember, it's understood to be base 10 equals log 30. So I can divide both sides by, so I'm going to factor out this x real quick. I'm going to have this x out front. I'm going to have x, and I'm going to have times what I have left behind, 3 log 5. Gives me log 30. So this log, I wrote this in a different color so you can see 3 log 5, that's a number. It's just some horrible irrational number. I don't want to write it down. It goes on forever, never repeats itself. So I'm going to divide both sides by 3 log 5. 3 times log 5. And when I do that, the x is going to be by itself, and I'm going to have x equals log 30 over 3 log 5. Now that I'm looking at this, there's nothing meaningful we can do with this. Log 30 doesn't divide into log. I can't divide log 5 into log 30. That doesn't make any sense. These are numbers unto themselves that are horrible decimals that have some relation to being some power of 10. There I have to, the log 30 is some power that I raised 10 to get 30 back out. So the easiest way to find out the approximate, so this would be the exact answer. So if Hawks asks for the exact, over here it wants the approximate. 2 p's in approximate answer. And that's when you approximate it. So you round it off, usually to anywhere from 2 to 4 decimal places depending on the instructions. So plugging this to the calculator, I'm going to take, like I said, it's just going to keep going back and forth. I can't stop it. I'm going to put in log. So I want my numerator in parentheses, so I'm going to say log of 30. And I kept my numerator in parentheses just in case. It's a good habit to get into. And divided by, and once again I'm going to include the entire denominator in parentheses. Otherwise it's going to divide it by 3, then multiply it by log 5. I'm going to close out that parentheses, and then I'm going to enter. And 0.70442 seems about the right number. Because if you think about it, try to think about your answers as you write them down. So if I round this to 4 decimal places, if I raise, so if 3 times this would be something around 2.1. So this would be 5 to the 2.1. That would be around 30. 5 to the 2.1, something like that. You could always check it by saying 5 raised to the, and then let's say 3 times 3 times, and then we'll say the answer, so second function, answer, and we hit enter, get 30 back out. So that checks our answer. And you should have to be able to have that power key on your other calculator, your scientific calculator as well. So that's your approximate answer. So you can always check your answers with these equations as well. So solving exponential equations, we isolate the exponential expression, take the natural logarithms or log of both sides depending, use the power rule to rewrite the exponents as coefficients, solve the resulting linear equation, and then the fifth step, give the answer as either an exact expression or a decimal approximation, depending on the instruction given. So here, this one has a little bit of arithmetic before we start. We have solve, our exercise 2 says solve 4 times 7 raised to the x minus 1 equals 36. I'm going to get rid of that 4 and divide both sides by 4 first before I start. So it's going to give me 7 raised to the x minus 1 equals 36 divided by 4 is 9. Now 7 and 9 don't have a base in common, so that's when I'm going to have to use my logarithms. And how many more exercises do I have? Is the next one a natural logarithm? Oh, I forget my place. I edit my slides. No, the next one doesn't. I'll use natural log for this one. So I'm going to take the natural log. You can use log of both sides. As long as you do it to both sides, you're fine. So the natural log of 7x. And remember, it's your choice. If you like to stick with log, you can stick with log. The only reason why you choose log over natural log is if you had 10 to some power, you choose natural log. If it was e to some power, that would be more likely. So doing that, we're going to move this x minus 1 out front. So I'm going to have, I think I'm about to have company. So I have x minus 1 quantity times log 7 equals natural log 7 equals natural log 9. I'm going to divide both sides by natural log 7. Remember, natural log 7 is some number. So that's going to give me x minus 1 on my left-hand side. That's going to be equal to natural log of 9 over natural log 7. Remember, they aren't in any significant ratio to each other. They are powers that we raised e to get 9 and 7. So it doesn't make any sense to try and simplify that. And you get the exact value of your equation being natural log 9 divided by natural log 7 plus 1. And over here, if we want the approximate answer, so this is exact. Oops, spelling exact wrong. It's not exactly how you spell it. And the approximate is going to be, we'll go to our calculator again. And so we're going to have something that won't focus. Natural log of 9 divided by natural log 7. And I'm going to add 1 to it, plus 1. So I get 2, 1, 2, 2, 9. No, just 2, 1, 2. I get 2.1291. Round that up to a 2 if you wanted to. Once again, you can always check this by plugging in and saying 7 to the 2.1292 minus 1 power will give you 9 back out. You can check that and it will check out. Alright, so now comes to the most interesting type of problem. This one probably the longest one you have on your homework is when you have exponents on both sides. But very quickly, to make sure you're in the right section, always make sure if you can get a like base, get a like base first. Here we have a 5, here we have 3, they have no base in common. So we're going to go ahead and say I'm going to take the log of both sides. Students tend to like log better. Not exactly sure why. Maybe base 10 is just easier to imagine in their head. So I'm going to get log 5 raised to 3x minus 1 equals log 3 raised to the x minus 2. So I'm going to take both of those out front. as coefficients. I have parentheses 3 minus x, sorry, 3 minus 1, sorry, 3x minus 1. Sorry, I'm trying to listen for people in the background to see if they need me at the same time I'm doing math. It's very distracting. I'm going to get x minus, so I'm going to have 3x minus 1 log 5 equals to x minus 2 times log 3. Easiest way to figure this out is to distribute the logs, and so I'm going to write this all in one color, where I'm going to have 3x log 5 minus log 5. So I've just distributed, remember log 5 is the number, I can add, subtract, multiply, and divide by it, so I just distribute it through my parentheses here from the left, or from the right. Do the same thing over here where I'm going to have x log 3 minus 2 log 3. So now I'm going to take all my terms with x's and I'm going to move them to the other side, one side, the left hand side. I'm going to take my constant terms and move them to the right hand side. So now I'm going to have 3x log 5 minus x log 3 equals, now I'm going to have log 5, move that to the right, minus 2 log 3. I know this looks very intense, but remember these are all numbers. It would just be solving a normal linear equation. It's just these all numbers are just horrible decimals I don't want to write out, because I'd have to write out huge decimals, probably to 10 decimal places, just being remotely accurate with this. And that's just a lot of numbers we don't want to keep track of. It's easier to write something instead of 10 decimals just to write it as log 5. But if you absolutely had to understand it, you could take log 5 right now and carry it through your calculation. If you carried it out far enough to as many decimal places, you would be correct. But it's easier to write it like this and then approximate it at the end. So now up front I'm going to factor out this x. So I'm going to x times, and then I'm going to have left behind 3 log 5 minus log 3 equals log minus 2 log 3, log 5 minus 2 log 3. Said 3 and I wrote 5. And then I'm going to divide both sides. Remember, this is a number, it's just some horrible decimal, so I want to write it out. So I'm going to divide both sides by 3 log 5 minus log 3. And when we do that, 3 log 5. Oops. So I'm going to get, ultimately, I get x equal to log 5 minus log 3, I'm sorry, log 5 minus 2 log 3 all over 3 log 5 minus log 3. And that's the exact answer. And to figure out the approximate, going to be, now this is where you have to be very careful with your parentheses and make sure you use them correctly. So now I'm going to get open parentheses log 5 minus 2 log 3. Then I'm going to close that top numerator. I'm going to divide it by the denominator. I need the denominator in parentheses as well. So 3 log 5. Close that log 5 out, minus log 3. Then I'm going to close out that an additional parentheses and hit enter. So now I have negative 0.15759. Probably round that off to negative 0.1576 to 4 decimal places. That would be your approximate answer. So in Hawks, in the courseware, they'll have a place where you can enter your answer in the exact form and then the approximate form. If one of those answer blanks is wrong, it counts the whole thing wrong. So make sure that you rounded off the correct place and you got both the exact and the approximate answer correct. All right. So remember, this looks very complicated, but it's just this number right here. It's just this decimal. We just haven't written it out yet until we evaluate it in our calculator, because we're going to have to round off at some point, because they're horrible, horrible decimals that go on forever and never repeat themselves. Next, solving logarithmic equations using the property of logarithms like we just did in section 7.4. To combine all the logarithms into one logarithm on one side of the equation, we convert the equation to exponential form. That's the second step. The third step, we solve the resulting equation for x. Fourth step, we check our answers. Remember that you can only take the logarithm of a positive number. Any proposed solution that results in either a 0 or a negative number inside the logarithm is an extraneous solution. So here are our rules, just to remind ourselves real quick. First rule, summary of our logarithms. First rule is y equals log base a of x is equivalent to a to the y equals x. Log base a of a to the x is equal to x. A to the log base a of x as its exponent equals x log base a of, fourth rule, excuse me, I should announce the numbers before I start. The fourth rule is going to be our multiplying on the inside is adding on the outside. So that's log base a of x times y on the inside of my log equals log base a of x plus log base a of y. Fifth rule, log base a of x over y equals log base a of x minus log base a of y. Sixth rule, log base a of x to the r power on the inside of my log equals r times log base a of x. So, looking at this first rule, all we have to do is convert this to exponential form, and it really quickly becomes apparent what we're doing. So we have our base 2 to the third power equals 5 minus x. We actually could have solved this one back in 7.3. We could have solved it there just by converting it from logarithm to exponential form. And then we're going to have 8 equals x minus 5, so that means that 13 equals x because I add 5 to both sides. And then you have to check. So I'm going to say log base 2 of 13 minus 5 equals 3. And really you can stop, most cases that I've seen, you can stop as soon as you check to make sure this is not negative inside the parentheses of your logarithm. Sorry, my little ones are running around in the background. Once you check that it's not negative, you can usually stop. But just to go all the way through, say this is log base 2 of 8. Well, 2 to what power gives us 8? Well, 2 to the third power gives us 8. So that's exercise 4. Exercise 5. So now we're going to have to condense these logarithms before we can evaluate them. Is it going to focus like that all the time? There we go. So I'm going to have to condense on the left-hand side and then set it and then put it in exponential form. So this is going to be log of, so I have log of x minus 3 plus log of x minus 2 equals 2. So I'm going to take that and say that's going to be log of x minus 3, and I'm going to multiply that times on the inside times x minus 2. So I'm multiplying on the inside because I was adding on the outside. That equals 2. So it's going to give me log of x squared, so x times x is x squared, x times negative 2, negative 2x minus 3x, multiplied my inner terms, and then my outermost terms, or my last terms, excuse me, plus 6, and that equals 2. So I'm going to get log, which is understood to be base 10, of x squared minus 5x plus 6 equals 2. And then now I'm going to convert this to exponential form, so it's actually the understood 10 power to the second, 10 to the second power. It's going to give me x squared minus 5x plus 6. Then once I have that, this 10 is actually 100, x squared minus 5x plus 6. And then I'm going to take this and I move this to the other side. And so now I'm going to get x squared minus 5x minus 94 equals 0. So now I need to solve this equation. In solving this equation, you'll find out if you try to factor this, 94 doesn't have a lot of good factors. 94 divided by 2 is 47. 47 I think is prime. Yep, it's not divisible by 3, it's not divisible by 7, it's not divisible by 5. So 47 is prime. So the numbers 2 and 47 aren't going to add to give you 5 in the middle. So you're going to have to use the quadratic formula. So let me do that in orange. So I'm going to say x equals, and so I'm going to have negative b, so it's going to be plus 5. So let's say this is my a is equal to 1, b is equal to negative 5, and c is equal to negative 94. So I'm going to get plus 5 plus or minus the square root of negative 5 squared, which is 25. I'm just going to write that. Minus 4 times 1 times 94 all over. And actually that's negative 94 all over 2 times 1. So x is going to equal 5 plus or minus square root of 25 plus 4 times, 94 is going to be, so let me just do this off to the side, it's 376 all over 2, so x is going to equal 5 plus or minus the square root of, this is actually going to be 401 all over 2. Apologize for the noises again. We have x equals 5 plus or minus, and that's about all we can do because 401 is not a perfect square. But if we wanted to approximately think of this, this could be the square root of 400 is 20. So this is actually approximately 5 plus or minus 20 all over 2. So basically you're approximately getting 25 over 2, which is going to be 12.5, or 15 over 2, which is 7.5. So those are your approximate answers. It's not going to be quite that, but those should be your approximate answer. If I plug either of these ones in, it's not going to be negative. Excuse me real quick. Apologize, my son could not find somebody, had to inform me of it. School will be starting soon. Keep thinking that. Alright, so these are my approximate answers. They're not the exact answers, but I can see if I plug either one of these in here, like if I said 12.5 or 7.5, 12.5, 7.5. And here, these will both give me positive values back out, so both of these answers will work. So this right here, both of these will work, and I can check them both out. And you can plug them in, you're going to see that they do work. So I strongly suggest you, if you're good with your calculator, go ahead and plug those into your calculator and show yourself it worked. But yeah, so you want to make sure that these numbers that you're getting here, which are both going to be positive, or sorry, excuse me, take that back. They're not both going to be positive. I'm sorry, I got interrupted by my son. Let me go back. So we get roughly 20 here. It's going to be 5 plus. This is actually going to be, when this is 5 plus 20, we're going to get 20. So we're going to get either 25 over 2, or we're going to get negative 15 over 2. So this is actually negative 7.5. So one of these is not going to work. I was pretty sure one of them wasn't going to work. And so this 7.5 or this negative version of this is not going to work. So this is not going to work. Only the positive answer is going to work. So the only one that works, our answer is going to be x equals 5 plus 400, the square root of 401 over 2. Now some students are probably like, wait, why is this so complex? Is that I like to show an example. Sometimes Hawks generates ones that don't have nice answers and you have to use a quadratic formula. Everything's the same. You're just going to have to approximate your values or use your calculator to check to see if them work. A lot of times it will work nicer if you don't use this as a power of 10, this 2 to the 10 power, you just set equal to 2 and solve. It might actually factor nicely then. I think it would factor into -4, -1. And so you'll think something, oh, it really works because you get nicer answers if you just let that equal 2 over here, your polynomial, equal to 2, your original polynomial, after you put it in exponential form. And so the real answer is a lot more complicated than the answer that would have been easier to find for students. And so I want to show an issue where you could get something really complicated. It looks like you might have done something wrong, but you did it right. And taking a shortcut like saying 2 equals x squared minus 5x plus 6 would actually give you an incorrect answer, even though it looks easier. But yeah, so you can get ones where you have to use the quadratic formula on, so be careful of that. But yeah, notice I only plugged in the approximated values. Once again, actually plug in the real values if you're going to check it with your calculator. Here's another one. We have the natural log. So here we say solve the natural log of, exercise 6, solve the natural log of 2x minus 5 minus natural log x equals natural log 3. Now here's an interesting thing we can do. So we can combine this, and we're going to say natural log of 2x minus 5 divided by x quantity. So I'm dividing the numerator 2x minus 5, and that's all over x, and that's going to equal the natural log of 3. I could move the natural log on the left hand side and put that in the denominator as well, and then set it equal to 1 or set it equal to 0, and then use the exponential notation. I can do that. But here, the natural log, since the insides both have to be positive, because I can't take the natural log of a negative number, I can set these equal to each other and solve. I'm just going to have to check my answer in the end. So when we do that, we're going to have we're going to get rid of the natural log. Basically, we could think of this as e to the natural log power to the power natural log 2x minus 5 over x, and e to the natural log of 3, and that's kind of how they cancel. So we're going to get 2x minus 5 all over x equals 3. So that means I'm going to get 2x minus 5 equals 3x. I multiplied both sides by x. And then that's going to give me, move the 2x to the other side. It's going to give me negative 5 equals x. So negative 5 equals x. Do we just assume that that's our only answer? That's the only one that works? No, we go check. We plug that in, we say natural log, and you have to plug it into the original equation, natural log of 2 times negative 5 minus natural log of negative 5. And right here we can already see we have a problem. We plug in a negative number here, and this is also going to be negative. It's going to be negative 15, so I'm going to have negative 15, natural log of negative 15 minus natural log of 5. That's going to be a big problem because they're both negative inside my natural logarithm, so that's not going to work. So negative 5, so it's no solution. And the empty set, maybe one of the symbols you can click as well. There's no number that will satisfy this, and the reason why is because when we condensed it, we generated an answer that didn't exist by those negatives in numerator and denominator were cancel, and so this is positive, so this makes sense mathematically here, but that's because we canceled our negatives when we divided on the inside 2x minus 5 by x, but we couldn't put it in the original equation. So always check your answer. Here we have applications. In section 7.2 we mentioned continuous and compounding interest, which grows by the formula a of t equals p times e to the rt. At that point we didn't have the tools to yet solve for t. Now we have the necessary tools. The quantity of a radioactive substance decays or shrinks over time and is modeled by an exponential curve with negative constant r. So looking at this, we have a common exercise, carbon-14 dating. And so in exercise 7 it says carbon-14 decays according to the function a of t equals a sub 0 e to raise to the negative 0.000121 t. We're giving starting amount. How long will it take until half of it has decayed? So it may give you various starting amounts, but we'll just say the starting amount is going to be 1. And so that means half of it is decayed. So that means that my a of t, I don't know t, but I want my a of t to be a half, and my a sub 0 is going to be equal to 1. So I'm going to say a half equals 1 times e to the negative 0.000121 t. And so all I have to do is basically take the natural log of 1/2 equals the natural log of e raised to the negative 0.000121 t. The reason why I do this is that I want to take the natural log of both sides so I can get that t and solve for that t. Before, when that t was stuck up there, we could only solve it. We had the same base. 1/2 and e don't have a base in common. And so I'm going to say the natural log of 1/2, and this just becomes the natural log of 1/2 equals, and e, and the natural log of e, what did I raise e to get e to the negative 0.00121t? I raised it to the negative 0.00021t power, and then it's a t. And then I'm going to divide both sides by the coefficient in front of it, so I'm going to get natural log of 1/2 over negative 0.000121, and that equals t. And then you plug it into your calculator. So we're going to have, focus, natural log of 1/2. You could say 0.5, that's the same as 1/2. Enter that, and I'm going to divide that by negative 0.0001, focus. Can I focus that close? There we go. Oops, I messed up. We get roughly 5,728.48, so that means T is equal to 5,728.4, and you can round that to 9, and then it'll probably say, we'll probably want you to round to the nearest year, if you can do that. And so it's going to take how many years? So they didn't tell you this, but the time is in years. So carbon-14, which usually carbon-12 is the non-radioactive form of that isotope, carbon-14, and that decays, it takes 5,728 years, roughly, for half of the amount to remain, and then it half-lives, so forth and so on. And every 5,000 years, basically 5,700 years, you'll have half the amount you had started for. So after about 11,000 years, you'll have a quarter, so forth and so on. But anyway, that's it for today's lesson, and I hope you all had a good one. And yeah.